Very much, Paul Herrling, for not only keeping to time, but also to give us an excellent example of a success story of one of these public-private partnerships. And he showed us the comprehensive story from the beginning to the end. And I mean, it's not registered now, but I think it has an excellent chance to become a new drug in 1 or 2 years. And as you mentioned, Novartis has another or 2 other molecules which are a bit behind or at similar stage. No, this is a great story, and it makes us look forward. Yeah, we should also look forward, and it's a pleasure to announce our next speaker. It is Xavier Fernàndez Busquets. He has a PhD in molecular biology, and he has very good links to Basel. I read that he was a trainee at Ciba-Geigy, that means a long time ago, and then also later on a postdoc at the Friedrich Mirscher Institute, which belongs to Novartis. Currently, he is a senior researcher at the Institute for Bioengineering of Catalonia in Barcelona. Please. Go ahead.
Thank you, Reto, for the introduction. I will try to build on Paul's talk by talking about ways to deliver antimalarial drugs as specifically as possible to target cells by using nanotechnology. And then when I start this talk, usually my colleagues raise eyebrows when they see together the words nanotechnology and malaria, because they always say, well, this is an oxymoron, these 2 things cannot be together. Because by looking at where most of malaria deaths occur, it's clear that nanotechnology, because the conception of it is that it's something expensive, should not be applied to diseases like malaria. Actually, this is a misconception, and I think most of us agree that nanotechnology is not yet this. It's not yet a small nanomachine made of mechanical parts that can interact with single cells. The second part is true, it can interact with single cells, but these nanomachines are made of macromolecules, 2, 3, 4 elements maybe, and this is not so expensive. But however, there is an economic bias in the story, which I think is still true. If you look at the causes of death, it's clear that in the developing world, infectious disease is prominent, which is not the case in the developed world. And this, of course, gives you a hint of where the money goes. And I just looked in the internet a few weeks ago. The NIH budget for 2013, only for cancer, is more than $5 billion. And then if you compare the global expense in malaria for all the planet, 2015, it will top at $2.5 billion, and the worst is that this is reaching a plateau. Then we will not have, probably in the near future, more money for malaria research. And it's even worse for nanomedicine. Actually, I didn't find any numbers for nanomedicine and malaria. The only thing I could do was to look in the Web of Science, and the 2 words together, you get only about 30 hits, and because 1/3 are from our unit, I can easily estimate that the global budget for nanomedicine applied to malaria is about $200,000 US, which means that we must work cheap, but this doesn't mean that we must work bad. The nanomedicines we design must work as the best, but always with this economic idea in mind. Then from the 4 pillars that we use today to fight malaria, namely vector control strategies, vaccines, diagnosis, and drugs, as we have seen before, we are focused on the drug part, but not specifically on identifying new drugs. We leave that for the big pharma companies that have more resources, but on ways to specifically deliver those drugs. As we have seen before, one way to avoid this evolution of resistance, which will happen probably with every single drug that will be reaching the market, is that because these compounds reach the parasite in relatively low amounts or not in sufficiently high amounts, some parasites survive and they evolve resistance. Then one way to avoid this is to find ways to deliver drugs in amounts as high as possible and as specifically targeted as possible to target cells so that you kill the parasite quickly. With this idea in mind, we started working with liposomes and had relatively good results with immunoliposome targeting, but then because liposomes are very bad for oral administration formulations, we decided to switch to other types of nanocapsules that could be more easily formulated as a pill. And here we started collaborating with the group of Elisabetta Ranucci at the University of Milano, who are experts in the synthesis of polyamidoamines, which have a good record of low toxicity, cheap synthesis, and they had been used in the past to encapsulate drugs, for instance, against AIDS. These polyamidoamines give nice homogeneous dispersions of below 20, 30 nanometers, which is what we need. And then when we apply this to a mixture of red blood cells, either infected by Plasmodium or non-infected, we had the good surprise that polyamidoamines did not need to have a targeting molecule like an antibody, but by themselves they enter Plasmodium-infected red blood cells, probably through a rather unspecific way, but this is the fact, and then this was very good. As you can see here, there are several normal erythrocytes, and the only one that has Plasmodium, this one is penetrated by polyamidoamines, and not only that, but this polymer binds the parasite. Something good about polyamidoamines also is that when you load them with antimalarial drugs, like in this case primaquine or chloroquine, the drug is released in a nice, smooth way along a 24-hour period. It would be bad if it leaks too quickly. It would also be bad if it stays in the polymer for more than 24 hours. In this case, those were very good news. And also, in vitro, it gave much better activity than chloroquine alone when we use same concentrations of the free drug and the encapsulated drug. The encapsulated drug is capable of eliminating parasitemia in vitro, and also in vivo, where chloroquine at a dose of 0.8 milligrams per kilogram per day is unable to cure the animals. The same dose encapsulated in polyamidoamines is able to cure mice. Then the prospects were very good. Also, it was interesting to notice that in terms of how expensive they were, this is what we use as a standard. How much does it cost to improve 10 times the activity of chloroquine for a liter of tissue culture or blood? The first immunoliposome prototype was a prohibitive 50 euros to get this improvement. With polyamidoamines, we went down to 40 cents of euro, and with some new types of polymers of dendrimeric nature, we are even below that. But those dendrimers, they are not so good in vivo. Then we look at what might be the activity of polyamidoamines in facilitating this entry of drug. Then it was clear that the polymers, as you can see here by the gold bits, they do penetrate Plasmodium-infected red blood cells. But then the other surprise was that in the absence of any drug, some of these polyamidoamines had antimalarial activity by themselves. And then this came also as a surprise. And then we were looking more in detail at what this mechanism of antimalarial activity might be. And we realized very soon that polyamidoamines do not only enter infected erythrocytes and bind the parasite inside the cell. It was also very clear that they have an affinity. These are individual merozoites of Plasmodium falciparum. As you can see here, this erythrocyte is not anymore there. The cell burst, and these are free parasites. And the polyamidoamines, one of them, they stick very well to Plasmodium. which gave us the idea that maybe because Plasmodium is a very fragile organism and it needs to penetrate red blood cells very quickly after it has egressed from an infected cell. If you prevent invasion, maybe by blocking the interaction of the parasite with the cell, that might be the mechanism of activity. But then, as a consequence of this, there is an obvious derivate, which is if you are able to keep the parasite without invading the cell, which means the parasite, as it's very clear here, this is a control where we'll do nothing, and we have the expected ring stages. If you add polyamidoamines, you see that the parasite does not invade, which means that it's more visible for the immune system, and in this way we think that these polyamidoamines could be a type of combination therapy, of not combining two drugs, but of combining first a targeting drug delivery strategy where the polyamidoamine brings the drug to the target, and then a second life as possibly a vaccination adjuvant. This we are exploring now with in vivo assays, but it seems to go in that direction. And then in my last minute, I will just mention what actually is the title of my talk, but it will be only one slide because it's in process, this work, and it's not easy. Every anti-malarial strategy is focused, as we have seen in Paul's talk, on the blood stages, but there is a consensus in the malaria community that transmission stages from human to the mosquito and vice versa are better targets because of a number of cells. But also probably the ultimate advantage is that whatever you develop for humans will have to go through clinical assays. If you develop something to be administered to an insect, the clinical assays might be significantly simplified. And this is what we are attempting to do. For that, we will need new nanoparticles, obviously, but also new drug types. We have some of them in mind, but because of patent reasons, I cannot explain them here. And I will, in my last slide, explain you what we did with mosquitoes. We fed them nanocarriers, these polyamidoamines, to see if they would kill the mosquito. This didn't happen. If once ingested by the animal, it would go out the same way they went in. This would be also very bad. It would be nice to see that they exit the stomach and they scatter throughout the insect's body. And this is actually what happens, and as you can see here, most likely after ingesting polyamidoamines, the polymers go to the salivary glands, which is a highly desirable target if we think about targeting sporozoites, for instance. And with this slide, I will thank the students who did this job and also our funding agencies, and thank you very much for your attention.